In the last lecture, we saw a new method, implicit beamforming method, for the case of one-dimensional advection equation of the form dou u by dou t plus dou f by dou x equal to 0. Through some manipulations and evaluation of terms, we finally got an expression for advancing from time step n to time step n plus 1 in this particular form, where we substituted space derivatives, where we evaluated the space derivatives using central differences to finally get an equation for ui n plus 1. In this form, it is implicit, therefore we had to evaluate ui n plus 1 in terms of u I plus 1 n plus 1 and u I minus 1 n plus 1, and these can be put in the form of a tridiagonal matrix equation. As we noted at that time, this equation has the capability to take account of nonlinearity. Since we are dealing with a single equation, the coupling aspect does not arise here, and this particular form can be put in a special form. So, we finally get an expression for u I n plus 1 in terms of u I plus 1 n plus 1 and u I minus 1 n plus 1, and as we remarked it in that lecture, the resulting equations are in the form of a tridiagonal equation, and we have to solve at time step of n plus 1 for all the values of ui for I equal to 1 to the end point where we need to find. So, this equation is of second order accuracy in both time and space. It is also implicit, and it is also a stable equation. Now, there is a special form of this called the delta form, which is actually more convenient to write and evaluate when we look at extension of this for 2D and 3D problems. So, we define delta ui as ui plus ui n plus 1 minus ui n here. This is at delta ui n is okay, we can also keep it like this and rewrite this equation here in this particular form. Okay, so, at nth time step or at n plus 1 time step, after we have evaluated ui n, this is the equation that we solve to get delta ui, and so this equation has variables not as ui n plus 1, ui plus 1 n plus 1, ui minus 1 n plus 1, but it has delta ui minus 1, delta ui and delta ui plus 1 as the variables, and this we can see is a tridiagonal equation. This is the tridiagonal form with coefficients of delta t a I minus 1 n by 4 delta x and a I plus 1 n divided by 4 delta x here and 1 here, and so this gives us a neat little form for the equations, and we can solve not for ui n plus 1 but delta ui here. So, this is known as the delta form of the implicit beamforming scheme. It is not any different, but it allows us to put it in a concise form. Now, if we want to extend it to 2-dimensional cases, then we have a governing equation like dou u by dou t plus dou e by dou x plus dou f by dou y equal to 0. It is like the previous case that we have seen for the McCormack scheme. Okay. But before we look at the full 2D viscous case, let us consider how we do it for the inviscid case, where we do not have the viscous stress terms here, and so E consists of only the convective or the advective terms. So, in such a case, we have U, E and F are matrices containing for the 3 equations we have the continuity equation, x momentum and y momentum equation. So, you have those specific forms here. So, this becomes a matrix equation, and this needs to be done rewritten in a matrix form, and that is what we have essentially done here. And this is written as I identity matrix plus delta T by 2 dou by dou x of A, and we will see what this A is, times I plus dou by dou y of B times delta U n equal to minus delta T dou E by dou x plus dou F by dou y n, where earlier we had A here which is dou E by dou U. We had this as A as has been given as dou F by dou U here. This A here is essentially dou F by dou U. Now we have the same thing given in a, this becomes a matrix type of thing. So, this becomes a Jacobian and this also Jacobian, whereas A represents variations terms which are coming with in the x derivative, B represents the terms coming in the y derivative here, and both are advective terms. So, these are nonlinear terms. So, the nonlinear part is linearized using in this particular way. Okay. So, this equation is something plus dou by dou x times I plus dou by dou y times delta ui n equal to this, and this is actually solved in 2 steps, like I plus delta t by 2 dou by dou x of a n delta u star equal to minus delta t dou E by dou x plus dou F by dou y n, and then once we get delta u star here, we put this here and then we solve this as I plus dou by dou y of b n times delta to, u n equal to delta u star. So, this is what is known as a operator splitting kind of thing. We will come back to this in module 5, but the advantage of this is here when we do dou by dou x of delta ui, we obviously get delta ui minus 1, delta ui plus 1 and delta ui, and when we put dou by dou y of delta u, again we get delta u j plus 1, j minus 1 and j. So, in the 2D case we have this equation consists not of I minus 1, I plus 1 and I, it consists of I minus 1 j, I j, I plus 1 j, and also I j minus 1, I j and I j plus 1. So, it becomes not a tridiagonal matrix, but a pentadiagonal matrix, and 3 dimensions you will have 7 diagonals here, and the pentadiagonal matrices are different obviously from the tridiagonal matrix, and in this particular case there are 3 adjacent diagonals corresponding to I minus 1 j, I j and I plus 1 j, followed by certain 0 diagonals, followed by the I j minus 1 diagonal and I j plus 1 diagonal. So, in that sense you have zeros in between some diagonals, and that is a typical pentadiagonal form that we get when we discretize a 2-dimensional equation. So, that is something that we keep in mind, and when you have a pentadiagonal matrix, then the tridiagonal matrix algorithm cannot be solved, but by first doing the x derivatives here, because in this equation the right hand side is evaluated at nth time step. So, this is all known here, and you have dou by dou x of delta u star. So, this will involve I minus 1 and I plus 1. So, that becomes a tridiagonal matrix equation here, and once this is done we get delta u star from this, and if you come to this equation, delta u star is now known from after solving the first equation, and then you have I plus dou by dou y of delta u here, and this gives us another tridiagonal matrix, but this time involving j minus 1, j and j plus 1. So, you can again solve this using as a tridiagonal matrix, and so this kind of decomposition is done because each step gives a tridiagonal matrix equation which we know how to solve efficiently, and we will deal with this in module 5. So, when we are looking at 2-dimensional case, we can do it as a pentadiagonal and then we can go ahead, but this operator splitting in this particular way helps us make use of the efficient tridiagonal matrix solution scheme that exists. So, this is one particular thing. Now, in this method, this looks a straightforward extension of the method that we have seen, and that is possible because what we considered to begin with is just an advection equation without any viscous terms, without any diffusion terms, but our Navier-Stokes equations do have viscous terms. Okay. So, for viscous 2D flows, the governing equation is not just the left hand side equal to 0, but we also have viscosity terms here, and here we are making a distinction between viscosity V1 and V2, and similarly FV1 and FV2. So, here we are writing the governing equations as dou u by dou t plus dou e by dou x plus dou f by dou y, advection term and then the temporal term, equal to dou by dou x of E and F are functions of u alone, and viscous. So, the E and F here are functions of u alone, and we have seen that dou E by dou u is A and dou F by dou u is B. So, that is where these things are, but here EF1 and FV1 are functions of u and dou u by dou x, and EV2 and FV2 are functions of u and dou u by dou y. Okay. So, these are viscosities. So, you have a second derivative. So, when you have dou u by dou y here, then you have that term here, and similarly you have dou u by dou x, and that is also coming here. So, in that sense it is just the same equation, but written in a special way, because we need to evaluate cross derivatives in a certain way and normal derivatives in a certain way, as we have seen for the McCormack's scheme. So, the same idea is being brought into this. So, having written this, how do we make up a solution scheme which is the beamforming scheme? So, we can write the implicit time marching scheme for the beamform as per the beamforming method as delta un equal to 2 delta by 3 dou by dou t of delta un plus 2 delta by 3 dou by dou t of un plus 1/3 of delta u n minus 1. So, this is essentially the time marching method. Okay. So, what we mean by this is you are evaluating delta u n, which is ui n plus 1 minus ui. So, you are going from ui n to ui n plus 1. So, in that sense you are marching forward in time, and this is evaluated in the beamforming method using a third order approximation which we have derived earlier for the 1-dimensional case. Okay. So, we are making use of that, and we have dou by dou t of delta un. So, dou by dou t of ui n plus 1 and dou by dou t of ui n, those will be coming here and they will be coming here also. So, and you have dou by dou t being given by this, just as we have done here. We have substituted dou u by dou t in as dou f by dou x from this equation as minus dou f by dou x from this equation. So, we are extending the same logic for a vastly more complicated case, and so if you do that and then if you do some manipulations, we finally get delta un equal to 2 delta by 3 dou by dou t of delta un. So, you have dou by dou x of delta En, that is coming from here, and then delta EV1 n plus delta EV2 n. So, these are the dou by dou x terms here, and then dou by dou y of delta Fn and then you have FV1 and F2N. So these are coming here, and then we can again substitute here. This is dou u by dou t, so we can directly put dou by dou x of En here, whereas in this case it is dou by dou t of delta un, so we retain this delta form of these. Here it is just dou by dou t of un, so we are directly substituting here. So you have minus En plus EV1 plus EV2 at nth time step, and that is what it is here, and then you have 1/3 of delta u n minus 1. Okay. So this is using, this is one form of the implicit beam warming scheme with the viscous terms. It is not yet finished because we need to evaluate these terms here, and this is also a system of equations, and we know that this system of equations has nonlinearity, and we also have coupling, and we have taken care of, we have taken account of this and taken care of this using through lagging, and what we have noted this down earlier, and we can also note down here. This coefficient matrix, this Jacobian here is being evaluated at nth time step, and therefore whereas this delta u here, or the delta u here is involves ui n plus 1, and this part here is therefore lagged. It is based on, although it is a function of u, it is making use of the u values at nth time step and not at n plus 1th time step. So in that sense this is an evaluation of the nonlinearity and coupling based on the previous time step values, and therefore this is called lagging. Okay, lagging. So this particular contribution of the overall equation here is coming based on the previous time step values, whereas this is based on the new time step values. So this enables us to write the nonlinear coupled equations in the form of linearized equations, and which enable us to explicitly evaluate the coupling terms. Okay. So the same logic is being applied here. It is more tedious. So here you have E here and F. You also have EV1 and EV2 and FV1 and FV2. So each of these is treated in a specific way. So we have delta En is written as An delta Un, and delta Fn is written as Bn delta Un. And why are we writing like this? Because A is dou E by dou U times delta U, so that gives you delta E, and delta F, B is dou F by dou U times delta U, so that again gives you delta F here. So it is a rewriting of these nonlinear and coupled terms in this way, where the primary variable ui n plus 1 is coming out in this unscathed in an implicit form, but the coupled coefficients and the nonlinear coefficients are evaluated based on the previous time step values, which we know. So this enables us to take account of nonlinearity and coupling, and this is done for different terms, the convective terms and the viscous terms, in different ways, and that is what is summarized here. For the convective terms, where that is E and F, which involve only U and not derivatives of spatial derivatives of U, like dou U by dou X, dou U by dou Y, those terms are not there in E and F, and that is the way that we have split this equation here. E and F are functions of U alone, whereas EV1 and EV2 are functions, can be functions of both U and dou U by dou X, and these V2 terms are functions of U and dou U by dou Y. So we are making a distinction among the various terms that appear in these equations, and these are being done in a different way. So you have as we have noted for the McCormack scheme, the evaluation of the viscous terms, these terms brings in the idea of normal derivatives and cross derivatives, and we should be able to go back. Yep, here we have dou u by dou x, dou u by dou y plus dou v by dou x, and so we have the once you put dou f by dou x here, then that this term becomes dou square v by dou x square, but this one becomes dou square u by dou x dou y. So this is a cross derivative and this is a normal derivative. So the same idea is being brought into play here, and the normal derivatives, that is EV1 and FV2. So because FV2 is dou u by dou y, dou f by dou y, so this is dou u by dou y, so that gives you dou square u by dou y square, and E term is appearing with dou e by dou x. So this will give us the dou square u by dou x square term. So dou square u by dou x square and dou square u by dou y square are normal stresses, and these are evaluated as, even these are functions of u. So you have dou e v1 by dou u at nth time step. So this is the lagged nonlinearity and coupling of the this part which depends on u, and then you have dou f by dou u x times delta u ux here, where x denotes the derivative with respect to x. So we are taking care of the fact of the idea that EV1 is a function of u and dou u by dou x, and so you have function of u here and function of dou u by dou x, and so those two things are coming here, and these are further written as, so this is now written as Pn and delta un, and this is written as Rn and delta ux, and so we can do further manipulations to get to this particular form. Similarly, delta FV2n is written as this, again FV2 is a function of both u and dou u by dou y. So you have this as dou f v2 by dou u evaluated at the nth time step times delta u n. So that gives us part of this delta f v2, and that part which depends on dou u by dou y is obtained in this way. So dou f by dou f v2 by dou u y evaluated at the nth time step. So this quantity is known here, times delta u y it should be. Okay. So so this is again written as q n delta u n plus s n delta u y. So you can see, and so that gives us another equation here. So S y is okay. So these are so as we mentioned, S y is dou by dou y of S here, and these are for terms which are V1 and FV2, EV1 and EF2, but we also have EV2 and FV1. Those will give us cross derivatives, and those cross derivatives are evaluated based on lagged coefficients like this. Okay. So once you do all these things, substitute all these things, then we get a jumbo expression for which is the beamforming scheme for viscous 2D flows. So you have I plus 2 delta 3 by 2 delta t by 3 times dou by dou x of A minus P plus Rx. So these are all things that we have seen here with some approximations, and the idea is that here you have this whole thing times this whole thing times delta un equal to the right hand side terms, all of which are E's and EV1s and the x derivatives, y derivatives and all those things which are coming at nth time step, and some of them are coming at n minus 1 time step, and all these things. So, all of the right hand side is known, and the left hand side is a product of I plus dou by dou x and dou square x. So, essentially the x derivatives, and similarly I plus the y derivatives dou by dou y and dou square s by dou y square. So, this can again be decomposed. Evaluation of this will again give us a pentadiagonal matrix, and this can be factored into only the x derivatives and only the y derivatives. Okay. So, this enables us to solve this equation in 2 steps, each involving a tridiagonal matrix. Okay. So, and that is a form here, and so we finally get un plus 1 equal to un plus delta un, where delta un is obtained by doing this, and this is obtained by solving this equation. Okay. So, the essence of the beamforming method is now for viscous 2D flows is given by these things, where the coefficients A, P and Rx, R and all those things, SS, Fs, all those things need to be evaluated either analytically if expressions are known, and if necessary numerically these have to be evaluated, which we will examine in the next class, next lecture.